Welcome to the second podcast on using partial fractions. What I first wanted to start with is just what we did in the previous podcast, just kind of quickly to go through it and see how it works. If we want to integrate something like this over here, this 3x plus 13 over these factors over here, I'm going to set it up into two fractions, or a over one factor and plus b over the other factor. I'm not going to go through it, but if you remember from the previous podcast, you need to solve for a and b, and one way to do that is to use this cover-up method. There are other ways to do it. But it turns out that when we do that, and you may want to stop and look at this if you're not sure how it works, a is equal to 28 over 7, which is 4. B is equal to negative 1. Once we have those values, we're then going to plug them in for a and b. So a is equal to 4, b is equal to negative 1. We then want to integrate what's left. And we can look at it separately or not, or you can just write the answers. Again, I always choose to put those constants out front, but that's just going to be a natural log of both of those. So 4 ln absolute value of x minus 5 minus ln absolute value of x plus 2. Good enough. Let's go to the next one. Okay, something different. What if there's a repeated linear factor? What if the problem looks like this, where you have an x plus 2 times an x plus 2? Well, in fact, the problem's really not going to look like that. It probably looks more like that, but we can think of it as x plus 2 times x plus 2. If we went to try and do what we did before, if I do a over x plus 2 and b over the other x plus 2, if I go ahead and try and solve for a and b, it's actually not going to work. It's going to end up with a system of equations that has no solution. So that doesn't work. So what do we do? Well, there is another way to do this, or the way to do this, and that is when you have something like a repeated linear factor, you're going to put that a over one factor, and then you're going to put b over the x plus 2 squared. If this was cubed, I would have a over x plus 2, b over x plus 2 squared, plus c over x plus 2 cubed. And so you do that whenever it's repeated. So our goal now is to solve for this a and b. But before doing that, let's actually practice the setup a little bit more. So let's come back to that. So let's say you're trying to integrate that. You see it's a fraction. It's been factored into that. So you want to use partial fractions. What's the setup? Well, the setup is going to look like this. I have a over x plus 3, and then I have that repeated linear factor. So I have b over x minus 1 and c over x minus 1 squared. What about this one down here? Well, I've got to factor it. It has to be in factors. So first what I'm going to do is factor it. And then I see there's a repeated factor here, x squared. So that's going to turn out to be a over x plus b over x squared. And then I have that factor x minus 1. And so I have c over that. Then the last one's pretty similar. It's just a over x and b over x squared and c over that. It's pretty much the same thing. Okay, let's go back to actually trying to figure out a and b from that first one that we looked at. Well, if I have that set up and I want to solve for a and b, what I'm going to do is I'm going to multiply both sides by that denominator x plus 2 squared. So it's going to look something like that. So certainly we can see that on the left-hand side, those are going to cancel. And on the right-hand side, I'm going to multiply that x plus 2 squared times a. Well, one of them will cancel. And when I do it times the b, both of those x plus 2s, or those x plus 2 squares will cancel. So what I'm going to get is something's going to look kind of like that. If you're not sure where that comes from, stop it and take a look at it. Well, now I'm going to distribute that a. And then I'm going to do what I've always done before in each of these, is you're going to match up like terms. In other words, the 6x is going to have to match up to the ax. So a is just equal to 6. That was pretty easy. The constant term 7 is going to have to match up with the constants over here, 2a plus b. But since I already know that a is equal to 6, well, that's pretty easy to do. And so I plug in that value for a, and I get b is equal to negative 5. And what I wanted to do quickly before we actually go ahead and figure this out is let's just make sure that my numbers are correct. Not a bad idea. So let's take those values for A and B. Let's put them back in and make sure that I do get the same thing. Remember what you're going to do for this. You're going to have to get a common denominator. So I got to multiply that 6 and the x plus 2 by x plus 2 over x plus 2. So it's going to look something kind of like that. Distribute that out, and sure enough, we get back to what we started with. So we're good to go. Okay, so let's actually go ahead and integrate this problem. So we start with that. We have the setup. We then solve for A and B. We get A is equal to 6, B is equal to negative 5. Well, we can see on that very first one here, if I bring the 6 out, that's not too hard to do. That's 1 over x plus 2. That's going to be a natural log. But the one on the right, well, I'm going to rewrite that, pull the negative 5 out front, bring that x plus 2, write it as x plus 2 to the negative 2, and then I'm going to do a substitution on the right. So that u is equal to x plus 2, du is equal to dx. So when I put those substitutions back in here, it's going to look like that. What's the integral of u to the negative 2? Well, that's u to the negative 1 divided by negative 1. Or in essence, we're going to end up with that. So when I go to integrate that entire problem, what I get is 6 ln absolute value of x plus 2 plus 5 times x plus 2 to the negative 1 plus c. That part wasn't too hard. Let's look at something a little different. What if one of the factors is not linear? Well, this is actually a lot harder when we go and do this. So let's follow this and see how it works. What I'm going to have to do is I'm going to take each of these factors, and if there's a linear factor, I just put c over that factor. But because this factor is quadratic, I'm going to put a general form of a linear factor, ax plus b, on top of that. Well, now I got to go ahead and solve that for a, b, and c. And what I'm going to do is, like we did before, multiply both sides by that common denominator, by that denominator. So that cancels there. Distribute it to that. The x squared plus 1 will cancel. And then I want to distribute it to that. And so the x minus 5 will cancel. So when all is said and done, it's going to look something kind of like that. We have the numerator on the left. We have that ax plus b times x minus 5. And we have the c times that. Go ahead and multiply out what's on the right. And then we have to match up what's on the right, what's on the left. So again, we do it by like terms. 6x squared is going to match up with ax squared and cx squared right there. Negative 13x is going to have to match up with negative 5x and bx. So that's going to match up with that. And then that constant 19 is going to have to match up with what's left, negative 5b plus c. So we end up with that. Once I've got that, I then know that a plus c is equal to 6. I know that minus 5a plus b is equal to negative 13. And I know that, well, that's what I know right there. I don't have to do anything with that. So what I have is 3 equations with 3 unknowns. So we need to find those values for a, b, and c. Do you remember how to do that? Well, there's a bunch of different ways of doing it. One way is to use matrices, which is what I'm going to do here. And since it's probably been a while since you've done it, I'm going to quickly go through it. I have these 3 equations. I want to solve them using matrices. So I'm going to enter equations into the matrices into my calculator such that, even before I do that, let's take this and write it. Make sure we write it correctly. So that's 1a. Make sure you put in a 0 if there's no b's. 1c is equal to 6. Then do the same thing for each. Negative 5a plus 1b, but there's no c's, is equal to negative 13. And then the same thing for the last one, 0a. Now enter those coefficients, 1, 0, 1, each of those into a matrix. I'm going to call it matrix A. Then those constants I'm going to enter into a matrix. If you forget the dimensions, remember this is a 3 by 3. This is a 3 by 1, rows by columns. So I'm going to create matrix A and create matrix B. I want to solve for matrix X. Well, the actual algebra to do that, and you may have forgotten that, but it's not a bad thing to remember, is if I have this equation and I'm solving for matrix X, I'm going to multiply both sides by the inverse of A. I'm also going to do it on the left side. An inverse times itself, that's like 1/4 times 4. The inverse is also the multiplicative inverse, is equal to 1. Well, that's equal to the identity matrix. But the essence of what we need to know is right here. The matrix we're looking for, X, is the inverse of A times B. So I actually went ahead and did that on my calculator, and this is what I came up with. Here's matrix A in my calculator. Here's matrix B. I did the inverse of A times B, and these are my answers. Remember, they relate to A and B and C. So A is 2, B is -3, and C is 4. So now, that's the hard part. Now let's go ahead and use those numbers and finish this off. So A is 2, B is -3, C is 4. That's what we had from before. So this is equal to this. Now let's go back to the problem. So this original problem now looks like this. Well, how do I integrate this? Well, this is pretty easy to do. First part I'm actually going to divide up into two parts. So I have this and that. Notice I pulled the 3 out front and then that last term here. Well, with a little substitution perhaps, or just looking at it, we can see that if this is equal to u, this is du, so du over u is ln. That's a formula for the arctangent of x, and that's ln there. So definitely not an easy problem to do. It involves an awful lot. One last thing. If the numerator is the same degree or higher, then you must divide out the fraction and use partial fractions. So I'm just going to quickly run through this. The degree on the top is higher than the degree on the bottom. You got to use polynomial division, another good thing to practice. Don't forget putting in zeros for terms that are not there. X cubed plus 0x squared plus x. Divide that out. Remember, we are subtracting. So I get x squared multiplied by x squared minus x. I'm subtracting, so I get positive 2x multiplied by 2, remainder of 2. So when you rewrite this, it's going to look like that. Well, that's now pretty easy to integrate. That's just going to go right to that. And that's the idea. Divide it out if you need to. Take care.